Okay, cool. Hello, I'm Shale. I'm working for ARM, so it will be industry talk, which will be less technical. So I'm presenting some work happening in ARM. We are trying to verify a new sort of ARM product. It's called ARM Confidential Computing Architecture, short for ARM CCA. So let's step in. So ARM CCA, it is a new solution for our partner to build confidential computing. Confidential computing, you can imagine, it is a way to computing a sensitive information in a confidential way. In that case, will enable our partner to build solution to, for example, processing healthcare information or potentially even military information in the public cloud infrastructure. In ARM CCA, it is a complete solution that including hardware, software, and protocol. But in the entire solution, the key part is what we have presenting here. That is the hardware extension. The full name is called ROM Management Extension. Short name is IME. In this new hardware extension, we introduce two new secure states. One is called ROM state. It's in the orange-ish to the left. That basically is what we're going to focus on this talk. Separately, in this new extension, we also introduce a new state called root state that will correspond to the monitor run on EL3. In the new ROM state, you can see in the diagram, there's a key component called ROM Management Monitor. It's basically provide a bunch of interface to allow the non-secure hypervisor to interact with with any ROM inside ROM state. This also provides some interface for the ROM to extract certain information they want. For the sake of this talk, you don't need to understand some of the content. For example, what is the measurement, what is attestation. If you understand what is memory mapping, that's fine. But all you need to know is for any end user who wants to use ROM, you have to explicitly trust RMM. There's no way you can bypass it unless you should not use that as part of your solution. So this leads to our part of the main talk. We want to provide some verification to make sure these products are correct. There are several criteria by us being correct. In these themes, we have let's talk about how we define themes. So we have pretty much two teams. One team is defining the specification, meaning defining what is the behavior of all the interface. We have a separate team, they're gonna use that they're gonna implement a software that's supposed to satisfy the specification. In particularly, the specification team, they wrote this specification in a way that is machine readable. So for us, as a verification team, our challenge is actually, we need to dealing with a moving target. The specification and implementation are still changing today, actually. Also, as a verification task, our challenge are very different with with academia, let's say. Our challenge is more about scaling. The specification are quite large. It's probably around hundreds page now. The implementation we're dealing with is around 10K-ish C source code. So there's three pieces of work we are conducting here. First of all, we want to verify the specification. We use a theorem proven, surprise, to sort of verify the coherence and to verify certain invariant in the specification. Second part, we use a model checker, CBMC, to check the source code actually satisfy the specification itself. Third part, in the CBMC part, we mainly focus on sequential functional correctness. Obviously, the general question people ask is, what about concurrency? We provide a sort of debugging tooling to allow our engineer to manipulate, to intersect the execution and to manipulate the interleaving by themselves. So let's jump to slightly more technical detail. What the specification looks like. If you go to our public page now, you will see our specification there. the specifications are written in a style as we call rule-based writing. This is very common for all ARM products or all ARM document. Quite often you will see some description, and to the left you will see a label that's basically say this is a rule. It must be held through certain criteria. And the second part is because we're dealing with a specification for interface, the specification engineer, they choose to define them in a pre and post condition pairs. You can see in the slides, probably a little bit small. Basically, there's a several pair of failure condition. So precondition is specify what is a failure you are checking. If they fail, they're going to return some error code. Otherwise, if there's no failure occur, you will reach the successful condition. That basically says the state after you execute the program. As I mentioned, the document is generated from machine-readable specification. What I show here is the PDF version. So the first question we're asking is, does the specification make sense? Obviously, it's human artifact produced by our engineer. It's English artifact to some part. Does it contain any ambiguity? Is it actually consistent? More importantly, since it is a security-sensitive component, does they satisfy certain security criteria? As I say, if we design something wrong, already have security flaw, then we're done. So in this particular case, we believe a theorem prover is a good way to conduct this study, particularly or this verification work. We have a specialist in HO4, that's why we choose HO4. The reason we choose theorem prover is they give us a way to rigorously examine and rigorously decompose the specification, and we can understand better of the specification. In particularly, we manually converting the IMM specification to an equivalent model in HO4. In this activity, we obviously check in the coherence of the specification, either by engineer themselves reading through the document, or by HO4 engine, because if you define some mathematic that's conflict with each other, the HO4 will cause the problem. With this equivalent HO4 model of the IMM specification, we further validate some property we want to check. One important property we want to check is a ROM-to-ROM isolation. As I say, this is a sort of a sensitive, security-sensitive component. ROM-to-ROM isolation, you can imagine basically you have two different applications inside ROM. They should never share any data, or they should never share any memory pages. This has to be achieved by our interface design. We prove that. Separately, we prove some property related to the specification itself. For example, we prove there's no undefined behavior in the pre and the post condition. So as we're dealing with a theorem prover, most of the cases you'll fail when you try to prove something. In the early stage, when we starting this work, if there's a fail occurred, it's very likely we made some mistake by our engineer in terms of in the HO4 model. But once we get more confident of our artifact, we actually start to find issue. Surprisingly, this is a report from our specification engineer. There are 25% of the track issue actually reported by us, which is quite a big achievement. We mitigate issue at a very early stage of the work. We also purposely choose no automation here. Despite I mentioned there is a machine-readable specification, but we purposely choose, we do not want any automation because we want to have an independent review of the specification itself. And separately, when we spot issue, we can quick fix in our HO4 model, while while the specific engineer, they might spend more time to review our fix, whether it makes sense to them. So we can sort of move slightly faster, potentially. So that is about specification. Let's move to the implementation itself. To summary, it is low-level software. Well, we're still using C as our language because it is hard. It is in components are very close to hardware, so we still have a lot of C engineer, so they prefer you implement as a C, and also many of our partner, they can only understand C, so we're still choosing C as our implementation language. As I say, it's a low-level software. It contains a lot of bitwise operation, a pointer manipulation. There's also slightly small portion of a handwritten assembly code. Separately, this piece of software have to deal with concurrency API call. The first question we're asking here is, does our C implementation actually correctly implement our specification? This brings to our second part of the work. We use a C-bounded model checking, short for CBMC, to check, to do this check. I can give you a lot of good reason why we use CBMC, but in summary, this tool are quite stable, have a really good performance. As I say, we have around 10K line, very low-level code. It's quite difficult for other tools to deal with that. And also, it can pass pretty much, I always say 99.999% of the C source code, which is quite good for us. We cannot limit our engineer what they write in their daily job. For this work, we have a different mindset. We want to deploy this in the CI/CD system. That means we need as much automation as possible. We leverage the machine-readable specification here. Given the machine-readable specification, because it's pre and the post condition pair, we can generate some sort of skeleton, sort of CBMC skeleton there, in the CBMC syntax or in C syntax. However, in the skeleton, there's a few holes. One is, in the specification, they use quite a lot of predicate. Those predicate some predicate just have no semantics, because those predicate, they sort of describe some kind of a low-level implementation-related property. It just doesn't make sense to give a semantics in high level. So in this predicate, they just have English description. For those predicate, we have to manually implement them to linking with implementation detail. Separately, we need to set up an initial stage so they can exploring all possible pre and post condition. For the result, we managed to check memory safety. This is by default. CBMC always check memory safety by default, which is good for us. Because of our actual work, we also verify the functional correctness here. There's a few caveats here I should mention. For the handful assembly code, our engineer already replaced by equivalent C source code. Separately, all the loops are bounded, so we don't have an infinite loop here. We can easily deal with a bounded loop. Bounded model checking. Which then let's move to the next topic. We managed to verify, or we check sequential functional correctness here. What about concurrency? There's a few topics here. We explore a little bit themes. First theme we explore is a deadlock. In the implementation, they sometimes will lock several pages in one command. This might lead to deadlock, because if you have a different command run parallel, they might lock in a different order. We use Ho4 to define a deadlock-free and also prove a deadlock-free locking order based on the structure of the RMM state. And then, given the locking order, we verified locking order in the implementation using CBMC with some help of a ghost state. The ghost state basically tracking the log history. And then we want to move forward. What about data race? We believe we can potentially do that similarly using CBMC and some ghost state, but we haven't have a concrete solution here. Which more important property we want to check is atomicity. It's proven to be very difficult because some commands are by design not atomic. So there are some commands they will read some non-secure pages, which are not completely controlled by the RMM itself. So those commands are just not atomic. It's even very difficult when we talk to the specific engineer. They have vague idea how to even specify what we mean by atomic. So this is sort of an open question for us. given all those open questions, we think, since we cannot give a very full verification set, can we just provide in some tool to our engineer to exploring the concurrency by themselves? That is what the what we call TFS come from. As I mentioned, they can intercept the actual execution of the implementation. They can manipulate some RMM states, and they can also change, more importantly, change in the interleaving decision, so they can explore interesting interleaving by themselves. This is also supplement for the CBMC verification. This tool are more targeting helping our engineer to in their daily work. So, which brings to our conclusion. Obviously, this is industry work. We want to find issue rather than verify something 100% correct. In fact, we can, from the point of industry, we cannot never say to our partner, this is 100% correct, because you will always find issue. You always find something. So our claim here is we try as much as possible to help our engineer to find issue. We must use more pragmatic way to provide a feedback. Last point, people will always ask what happened to end-to-end verification. Obviously, it will be very ideal. Everybody wants end-to-end verification, but in this particular case, we even don't know what we mean by end-to-end, because we're dealing with something low-level software. Are we only thinking end-to-end is the software stack, or are we thinking is hardware combined with software? Even in hardware, do we only think architecture level, or do we think microarchitecture level? We have no clear mindset here. That's pretty much everything I want to present here.
Let me start us off with a quick question. So, a very cool work. It's astonishing to see how much tooling is needed to do this kind of work.
Yeah.
Do you have a sense of how much of it might be reusable or repurposable for future designs?
That's a good question. I mean, obviously for the theorem proof of side, you always have case by case. But for other part, for example, the CBMC part, we're using a lot of automation. As long as we have a ground truth that is machine readable, those things can be reapplied to other type of software we provide. For the last tooling, this is actually built on top of some existing tool inside ARM, so that is already being reused in other part of other kind of a project inside ARM.
Yeah, I have a question about the undefined behavior. You mentioned that precondition and after condition, there's no undefined behavior.
Yeah.
But this is tricky because C's undefined behavior are undefined, right? We have by we, I mean, all we collectively developers or engineers. We know there are tons of undefined behaviors and people have a good list of undefined behaviors, but to the best of my knowledge, no one claims they have a full list of the undefined behaviors for C. So then, I'm curious, what is your list of the undefined behavior you can claim?
Yeah.
You don't have an undefined behavior.
I think it's more about, because we are defining the interface in the pre and the post condition, we want to make sure we cover all the possible pre condition, and for all the possible post conditions, actually, you have a valid post condition. That is what we mean by undefined behavior. It's probably slightly different with when you're talking about hardware undefined behavior. This is more about the quality of your specification itself.
Okay, one last quick question.
Thanks for a cool talk. Are there any plans to try to do concurrent verification of the C code as well? And if so, have you looked at any of the concurrency verifiers out there?
It's a good question. We don't have a concrete plan, but the observation here is concurrency is just way too hard, and we want to provide a tool for engineer to use, because we only have a limited verification engineer in ARM. We can't just spend hundred hours to chasing what they have to change in, so we have to use more automation. We do not see any existing tool enable us to do more systematic concurrency verification. And also, as concurrency, you always have a problem of search and space just explode. Combining our code base already 10K, it seems not very practical at this stage.
All right, thank you.